Hey everybody, and welcome back to another lecture video. This time we are looking at chapter 12, and this chapter looks at intermolecular forces and the results of those intermolecular forces, which amongst other things are liquids and solids. So we're going to refresh a little bit about those phases of matter and then talk about not just the effects of these intermolecular forces, but also where they come from. So we'll start off by talking about a water droplet and the shape of a water droplet. Now, the spherical shape of a water droplet, now in space it would be spherical. The reason that it is teardropped, and this goes for fire as well, for flames, is because of gravity. And so otherwise in space these things would be spherical, fire and water molecules included. And the reason that these things would have a spherical shape, or in the case of maybe not so much fire, but water, is caused by the intermolecular forces. These are attractive forces, and they exist among the water molecules. Now, the specific interaction between the molecules, in for example, coffee that tastes bitter and the taste receptors on the tongue, is a cause of intermolecular forces as well. So when you taste something, the intermolecular force is what signals your body that you're detecting something. So a coffee molecule, let's say of caffeine, or one of the flavor molecules in a particular coffee strain, would interact with these same intermolecular forces that are holding water molecules into a spherical droplet. Now, living organisms depend on intermolecular forces for many of our physiological processes. Less specific intermolecular forces exist between all molecules and atoms. So there are very specific interactions that occur in our bodies, let's say between an enzyme and its particular molecule that it acts on, or a taste receptor and the specific molecule that you're tasting. We actually have to have taste receptors to detect molecules. Now, you don't have taste receptors for water. It wouldn't make sense. Everything is in water, and water is everywhere. You'd just be tasting water all day. Some population of or some percentage of our population actually doesn't have a taste bud to detect cyanide, or is it arsenic? It's one of the poisons. But evolutionarily, there is a subset of humans that do have the ability to taste this, and this is probably because it was present in something that they were eating, and so people that were able to detect it were able to stop eating the food that contained the poison, whereas others weren't, and so that got passed down, and now there's some percentage of our population that has the ability to taste one of these poisons that most people don't have. So those are specific interactions. The intermolecular forces that we are going to look at are the less specific kind. Now, these intermolecular forces are responsible for liquids and solids. So the state of a sample of matter, whether it's a solid, a liquid, or a gas, depends on the magnitude of the intermolecular forces relative to the amount of thermal energy. So let's just take a minute and let me give you a little bit more of an explanation. So let's take a look at a water molecule. Now, we remember from chapter 10 that this has a bent molecular geometry. It has a tetrahedral electronic geometry because it's got some lone pair electrons. Now, the intermolecular forces that we are discussing here are not any of the ones shown here. What we are looking at with these lines and these electrons are intramolecular, meaning within a molecule. And these are usually ionic or covalent. And these are strong. Now, what we are talking about in this chapter is intermolecular forces. So that would be the forces between molecules, inter rather than intra, intermolecular. Now, this is going to be the attraction between water molecule number 1 and water molecule number 2. And so these are much, much weaker. They're weaker. Because they don't involve shared electrons or even full charges, right? What the things that hold together, let's say salts, when we have an Na plus and a Cl minus, this is held together by opposite charges, and that's actually a pretty strong force, relatively, speaking. That is strong compared to what we're looking at here. In fact, ionic ones are the strongest that we see, more so even than covalent compounds. Ionic compounds tend to have much higher melting points and boiling points. So we're not talking about intra, we're talking about inter. Now that we've got that sort of out of the way, let's talk about something else. So let's use water as an example, and let's say that when we have water as a solid, right, let's just focus on temperature right now. So let's table the discussion on intermolecular forces. So right now, we're not dealing with intermolecular forces. We are just looking at temperature. So solids can be warmed up, right? We can add energy. And let's say ice, in this example, can become a liquid. And in this example, it would be water. So we can add energy and turn a solid into a liquid. Now we can also add energy to the liquid. And this would turn the liquid into a gas. And in the case of water, we call that steam, or we call it water vapor. Okay. So we clearly see that energy can affect the state of matter. We know that the molecular motion, how much motion the molecules have, is what temperature is. So when we continue to add energy to ice, when it hits 0 degrees Celsius, it starts to turn into a liquid. Right at 0 degrees Celsius, ice solid turns into liquid when we're talking about water. And as we continue to add energy, the temperature of that water is going to rise and rise and rise and rise until when it hits 100 degrees Celsius, it's going to transition into steam. Now, the reason that there are temperatures where these transitions take place has to do with the competition between the intermolecular forces and the temperature. Now the temperature, again, is just, we can think of it as the energy, let's call it kinetic energy. It's the kinetic energy of the molecules. Okay, so well, let's take a different example while we're looking at water here. And I think I have, what do I have as an example? I'm going to have to do a quick looking up something real quick, so bear with me. Okay. Isopropyl alcohol. No, acetone. Let's talk about acetone. Most of you know what acetone is. So when we have acetone becoming, gasetone, that's not what it's called, gaseous acetone, this happens at 56.1 degrees. Liquid to gas. So just as a comparison for our discussion here as we're talking about the competition between thermal energy and intermolecular forces. So now we are talking about IMFs again. So what I'm saying is, why does water have so much more thermal energy before it turns into a gas, right? Because if temperature is just a measure of how much energy your molecules have, then 56.1 degrees is a lot less energy, a lot less motion than 100 degrees. So acetone, with a lot less motion, can turn into a gas where water still can't. And it takes a lot more energy to get water up to what we would call the right temperature, to where it now has enough energy that it can turn into a gas. And so the reason for the difference is that water has a lot stronger IMFs than acetone does. Acetone, just for comparison purposes, let's say has lower IMFs. So same temperature, same energy being added to both of these different liquids, one of them will turn into a gas before the other. And this has to do with the relative energy that it takes to separate these molecules from each other. Remember, the water molecules are kind of holding on to each other through some force that we haven't looked at yet. The one that keeps water droplets spherical and the one that exists between molecules. Okay, so the molecules and atoms that compose matter are in constant motion. The energy associated with this motion is called thermal energy. The weaker the intermolecular forces relative to the thermal energy, the more likely the sample will be a gas. So when IMFs are, lower than, let's call it, the thermal energy, then this usually means that we have a gas. When we have stronger intermolecular forces relative to the thermal energy, the sample will likely be liquid or it will be solid. And so when we're talking about thermal energy, let's just pick a temperature, right? Because that's what, we all need to have a temperature to reference it. So let's just call it room temperature. So at room temperature, take a look around where you are. Most things you'll notice are solids. There's obviously a lot of gases in the air that you can't see, but the most of the matter, right, that you're looking at, that you're interacting with, that you have around you, is going to be solid. Very few liquids you'll notice. You might be sitting next to a big giant fish tank or an aquarium or something, and then I'm not speaking directly to you, but even if you are around some liquids, you'll notice that they're usually just water, right? In fact, most solutions, most liquids that we interact with are water solutions with things dissolved in them. And this goes for milk, this goes for blood, this goes for, unless you have a pure solution of something like rubbing alcohol or acetone. Most things actually are solids or they're gases, and very few things are liquids. The things that are liquids obviously have a little less intermolecular forces than the things that are solids. So the chair you're sitting on, those molecules that are holding on to themselves are able to stay a solid and not fall apart or melt, right, at this temperature, whatever temperature it is that you're listening to this or watching this video. You would have to raise the temperature of that material a lot to get it to melt. And so, we're probably pretty lucky that that's the case. Oxygen, on the other hand, is already a gas. Think about how lucky we are that that's the case. What if it was so cold on this planet that oxygen was actually a solid, or if it was a liquid, and we couldn't breathe it as a liquid? We had to go and stick it in a machine that would warm it up and vaporize it so that we could breathe it. We live in a cool environment where a neat environment where everything we need is the right phase, exactly the right phase for us. Water exists in a liquid phase, even though it should, by all accounts, be a gas. Okay, so I went off on a little bit of a rant here. Let's continue. So let's talk about the properties of liquids and solids, just to remind you what they are. In contrast to gases, in which most molecules or atoms are separated by large distances, the molecules or atoms that compose the liquids and the solids are in close contact with each other. So lots of space for the gases, no space for the liquids and solids. Now the difference between solids and liquids is the freedom of movement. And in liquids, even though the atoms and molecules are close contact, they're still able to move around each other. In solids, those atoms or molecules are actually fixed in their position. So although there is thermal energy that's around, it causes them to vibrate, maybe even spin around in a fixed point, but they are unable to move around each other. And then if you remember from chapter 11, gases, just the last chapter, they have low densities compared to liquids and solids. They have an indefinite shape. They take the shape of their container. They have an indefinite volume, relatively weak intermolecular forces. So let's just call them. So things that are gases, by definition, have weak intermolecular forces, because at this temperature, just the regular motion of the particles at 37 degrees Celsius or 79 degrees Fahrenheit, whatever temperature you're at, That's enough for them to break away from each other and not be clumping up, forming liquids, clumping up, forming solids. Liquids and solids have high densities. Liquids have the indefinite shape, but they have definite volume. Liquids have moderate intermolecular forces. So let's just say, let's just say moderate. And we're going to say that solids have strong or high intermolecular forces. Solids also have high densities. They have definite shape, definite volume. And they can actually be crystalline or amorphous. Crystalline being ordered, amorphous being disordered or with no clear pattern. So because the molecules in a liquid such as water are free to move around each other, they flow, they assume the shape of their container, right? Any container you put water in. But as far as solids go, especially those that are crystalline, like water tends to form when it freezes, these molecules are fixed in place. They do vibrate, so we don't say that there's no motion. Now let's talk about some of the effects of intermolecular forces other than the one that we looked at already, such as circular or spherical droplets of water. Now this one is the same as the spherical droplet of water. It's called surface tension, and maybe you've seen this phenomenon, things being able to kind of balance on the top of water. This paperclip is not floating. Things that float have a lower density than water. This has a higher density. Aluminum has a higher density, or whatever this piece of metal is. This would sink if you push it into the water. Now the reason it isn't sinking though is because the water itself is holding on to all the other water molecules and creating a sort of a barrier to that paperclip. There are bugs that take advantage of this. Certain leaves are able to, I guess maybe not leaves, because again, density plays into it. But anything that has a higher density than water that can do this is taking advantage of the surface tension. Let's talk a little bit about how it works. Again, before we move on, I just wanted to make it clear, without intermolecular forces at all, everything would be gaseous. Everything would be a gas. There would not be solid and liquid matter. So one of the most important things about intermolecular forces is that liquids and solids exist. Now, after liquids and solids, we see several manifestations, and usually we see these in liquids. So let's talk about them. There's the surface tension, and then there's another one that we'll look at that has to do with the flow of a liquid. So this is surface tension. The reason that it works is because if we look at the molecules at the different levels of the different layers of the water, we see that an internal water molecule has, let's just say they all have some amount of attraction. And I usually get by with this example. This water molecule here has energy to which it can attract other water molecules. Now it's hard to picture that, so I'm going to give you a number analogy and then I'm going to relate it. So let's just say that this water molecule here has $6. And he can share it with 6 friends. He can share $1 this way, this way, this way, this way. This is in 2 dimensions. He can also go in all 3 dimensions, so backwards and forwards and whatever. So this one water molecule shares $1, right? $1 each to each of these water molecules. Now let's say that you're this water molecule up here. You still have $6 worth of energy that you can share with your neighbors. But because this water molecule doesn't have any above neighbors, it only has neighbors to the sides and down. I don't even know what the math on this would be. What is it, $1.50? So this one can share $1.50 actually with each of its neighbors. Now let's switch that from money to being like an attractive force, like you're a magnet and you can only stick so many magnets around you, the magnet force isn't infinite. If you put too many pieces of metal on a magnet, eventually that last piece of metal you put on won't stick on there. And so this water molecule, because it has fewer neighbors to attract to, each of those neighbors gets a slightly stronger attraction because it still is going to spread out that money, that attraction force in all the directions it can. It's not just going to go, oh, well, I've got, some unused money, I'm just going to hold on to it. That's not how it works. So it spreads out. So that just means that all of the surface water molecules, they all just have a slightly tighter bond or grip on each other. Imagine them all just holding hands. They have a tighter grip. So things laid on the surface might actually have a hard time breaking that grip and making water molecules let go of each other. So that's what surface tension is, and different liquids have different surface tensions. You can swim because of surface tension. If there was no surface tension in water, it would be like trying to swim in gasoline. You'd go into a swimming pool full of gasoline, and then you'd try to swim out, and it's just like swimming in air. You would be waving your arms down, trying to push off, and the gasoline molecules would just get out of the way, and your hand would just like go right through them, and you wouldn't get any lift from it. You wouldn't be able to push off of it. So we love that water can do this. I don't know about the gasoline in the swimming pool thing. I don't know if that's true or not. Gasoline does not have as much of a an attractive intermolecular force as water does. So presumably it would be very difficult to swim in gasoline. I would imagine that you couldn't. But I also heard that milk is also very, very thin in that way, in that if you had a big enough tank of milk, you would also just sink to the bottom and be unable to swim out because of the lack of intermolecular force. Viscosity is the other one. Viscosity arises from this intermolecular force as well. It's the resistance of a liquid to flow. So liquids that are viscous flow more slowly than liquids that are not viscous. Motor oil is a more viscous substance than gasoline. Maple syrup is more viscous than water. I could write that. Motor oil, more viscous than gasoline. What did I say? Maple syrup? Greater viscosity than water. Viscosity is greater in substances with the stronger intermolecular forces because molecules can't move around each other as freely. There's also long molecules, such as hydrocarbons in motor oil. This has really long, what we call carbon-hydrogen chains. Each one of these kinks is a carbon, 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 and so on. And then all of these carbons have hydrogens on them. These are called hydrocarbons. And hydrocarbons make up waxes, they make up oils, they make up all the things that we burn for energy. These things, because they're really long, even though they don't have strong IMFs, they tangle really easily with each other and get all wrapped up. And that also is a reason why things can be viscous. So viscosity has to do with increased intermolecular forces, but it also has to do with increased length. I don't know if that's not how you spell length. That's not how you spell length either. Increased size. And it's not really increased size, but increased length. You know what I'm going for. Okay. Let's talk about one of the other parts that has to do with the intermolecular forces, evaporation, condensation, and thermal energy. So the rate of evaporation, or vaporization, as it's also called, increases with the following. Increasing surface area, increasing temperature, decreasing intermolecular forces, and let's kind of discuss that a little bit. So liquids that evaporate easily, okay, are termed volatile. Doesn't mean that they explode or that they burn. It just means that they evaporate easily. So gasoline is volatile, is also flammable. Water at 100 degrees is volatile. Spilled acetone is volatile. And actually even water at less than 100 degrees, and we're talking about 100 degrees Celsius, it takes 212 degrees Fahrenheit to boil water and turn it into a gas. Yet, if you go outside right now and pour some water on the cement, it's going to turn into a gas really, really quickly. And that the cement doesn't even have to be 200 degrees. You can go and actually leave your water in the cup out in the sun and it'll still evaporate. And the temperature outside is not 212 degrees. So water is volatile. Most liquids are volatile. But what we're talking about is that to make things more volatile, and this is only true for things that are volatile, there are also non-volatile substances like, let me think, I would say maple syrup is probably not very volatile. Or honey. Honey is probably not very volatile. If it has water in it, it's going to be somewhat volatile. But there are lots of liquid. Mercury is a liquid, not volatile. Okay. Liquids that evaporate easily are termed volatile. Now, to increase the rate of vaporization, we can increase the surface area. What does that mean? That means if I have a little kiddie pool, okay, little kiddie pool full of water, and I have and I measure the evaporation rate, and it looks like just whatever the amount of water that evaporated is some such a number of moles per second or whatever. We could measure it however we want. If I want a bigger evaporation rate for the same stuff, water, I can have a bigger surface area, so a bigger pool. And think about why that works. Only the surface area, or only the water molecules on the surface, okay, are the ones that are sort of held less tightly than those in the interior. The ones on the interior are, for one, they're nowhere near the surface where they can become a gas, and they're being held from all around. And we did say that the molecules on the surface had a stronger attachment to each other because they have less to go around, but that also generally means that they have less attachments in general. So they can evaporate the easiest. So it's the surface ones that can go. So by increasing the amount of surface you have, you increase the amount of molecules that have a chance at evaporating. Okay, what about temp? If we look at the temperature, we see that at a given temperature, a sample of molecules or atoms will have a distribution of kinetic energies. Okay, so what does that mean? If we look at this table here, we see that at the low temperature, so the graph in blue, all of the amount of molecules are listed here and the amount of energies they have. So let's kind of take a look at what this means. It says that, so as far as fraction of molecules go, there's a really, really high fraction of molecules that all have about this much kinetic energy. Now there's a smaller fraction, like right here, of molecules that have much lower kinetic energy. And there's also an even smaller fraction, right, of molecules that have high kinetic energy. And not just enough to evaporate, because that's what this line, this dotted line here is the minimum amount of energy needed before you can break free and turn into a gas. But there's even more that have beyond that amount of energy, and you can see it gets smaller and smaller. All the way out here, it's just the tiniest little fraction of the total molecules have enough energy. But there is some amount. Now, let's evaluate this a little bit more. So you can see here that the blue line has some amount of molecules that are able to evaporate at whatever temperature that is. Now, as we increase the temperature, we see the graph change, the curve changes. For one, right, the largest fraction actually shifts. So at the lower temperature, most of the molecules had energy, let's call it A, but now at the higher temperature, most of the molecules have a temperature B. It's a higher kinetic energy. Sorry, B is the energy, not the temperature. And so the fraction has gone down, but that's not. It's still the same number of molecules. We'll see that the graph also got wider. It got wider, right? And the portion of the molecules that had enough energy to escape has also gotten bigger. You guys know this. The hotter something is, the easier it's going to evaporate. So these are the three things, these are the two things so far. Surface area, temperature. Now, in addition to temperature, we're going to talk about intermolecular forces. Before we talk about intermolecular forces, let's talk a little bit about what condensation is, because condensation is the other side of evaporation. So when evaporation happens, molecules turn into a gas. Now, if you have a closed system, you eventually build up something called an equilibrium. So if we cap this bottle, initially there's no vapor in here. It's all just liquid. So then evaporation starts to happen. And as evaporation builds up, the vapor builds up. As the evaporation process happens, vapor builds up. So now we have vapor building up. Now every compound, every molecule that turns into a gas has a different equilibrium that it exists in terms of its liquid and gas phase. Liquid and gas. In fact, we saw in the last chapter that water vapor was temperature dependent, and we can actually go look up a table and see what temperature our water is to know how much vapor pressure there is, how much water essentially has turned into a gas. So let's just say at, if this is water and this is like 30 degrees, that there's a certain level of water molecules that are going to exist inside this gas, inside this container. When that happens, we start to see water molecules then starting to recondense, so turn back into a liquid. And this will happen at a slow rate initially until there's more and more molecules of water up here. But eventually, when we hit that limit, that at that temperature, we're going to see an equal number of molecules jumping up into gas phase as dropping down into liquid phase. And so even though these processes continue to happen, they continue to evaporate, they continue to condense, the amount of water molecules will actually become constant. So we reach a point where the amount of water molecules, even though they're constantly changing and turning back into a liquid and turning into a gas, is always the same. And we call that the vapor pressure. So the vapor pressure is the partial pressure of its vapor in dynamic equilibrium with its liquid. Okay. So vapor pressure is actually the feature that we can measure, because we've been talking about evaporation rate. That's something you have to look at and monitor and count and then figure out what the rate was. Vapor pressure is something that we can just describe across different compounds based on their intermolecular forces. So vapor pressure, again, is related to evaporation, okay? Where evaporation is the process of liquid turning into a gas. Vapor pressure is telling us how much of the gas is in the air. And it's something that goes up with increasing temperature, just like evaporation did. It also goes up with, actually it's independent of surface area. So the vapor pressure of water is going to be true for a small amount of water, a big amount of water, or just the ocean. We can even talk about the vapor pressure of the ocean. That's what's good about vapor pressure, is because it's independent of surface area, and it has to do with an equilibrium that's true everywhere. So vapor pressure is better to talk about than evaporation because it gets rid of the surface area aspect of it. The other thing, though, was the intermolecular forces. So let's talk about those. So vapor pressure decreases. That's not how I want to say it. It decreases with increasing intermolecular forces. And that should make sense. If I've got, now going back to the acetone and the water example, if I have a container of acetone and a container of water, and these are both at the same temperature, so let's say 80 degrees Fahrenheit, I'm actually going to see a much higher vapor pressure in the acetone. And we already had said that at the same temperature, we saw that it boiled at a different temperature. Remember, we saw that acetone boiled at a lower temperature than water did, that it took more energy to get water to become a gas because water had a higher intermolecular force. We would still see that here with vapor pressure. Because water has a higher intermolecular force, it would have the lower vapor pressure. There would be less water molecules in the air than we would see for acetone, which would have a much higher vapor pressure and more molecules. And again, higher vapor pressure because it has a lower intermolecular force. Now, we haven't looked at the intermolecular forces yet. You don't know that acetone has a lower one yet unless you've looked at those. And we're going to do that. Before we do that, we're going to look at a heating curve and then we'll move on. So a heating curve, with a heating curve, the temperature of water as it is heated from room temperature through boiling, and during boiling, the temperature actually remains 100 degrees until all the liquid is evaporated. So what you can see here is that the temperature doesn't just increase constantly. So since evaporation is endothermic, when a liquid is converted into a gas, it absorbs heat because energy is required to break the molecules away from the rest of the liquid. So our bodies use the endothermic nature of evaporation for cooling. When we overheat, we sweat. Our skin becomes covered with with liquid water, and when this water evaporates, it takes heat from our bodies so that it can break free of the water that it's connected to and go into a gas. So that cools us down. Now, high humidity actually slows down evaporation because high humidity basically means the water is already in the air. And so that's going to prevent any new water from going into the air. And so that makes it harder to cool down. There's already high amounts of water vapor, so the sweat doesn't evaporate as easily. Now, let's see. Condensation, on the other hand, let's see, do I have a graph I was going to show you. I guess we haven't gotten to condensation yet, but condensation is the opposite of obviously the backwards curve here. And so if this direction is endothermic, obviously this one will be exothermic. So as steam condenses, especially like if you've ever had steam condense on your skin, you'll see that it's very hot and it burns actually a lot more than the water would have. And that's because you get burned twice. You get hot water on you in the form of 100-degree water, but you also get steam. And when steam turns into water, it releases a lot more energy because that's the difference between a gaseous water molecule and a liquid water molecule is basically how much energy they have. So that process of landing on your skin and turning back into a liquid releases that heat onto you. The exothermic nature of condensation is actually also the reason that winter overnight temperatures in coastal cities, which actually tend to have water vapor in the air, don't get as low as those in the deserts that have dry air. And as the temperature drops at the coastal city, water condenses out of the air and that releases heat and it prevents the temperature from getting too low. In the desert, where there's little moisture, there's not a lot of water condensing, and so there's not a lot of heat being released, and so the temperature drop is a lot more noticeable. So coming back to this graph here, as we heat up liquid water, as we add heat, the temperature rises until it hits the point where it's going to start turning into a gas. Now, this flat part of the curve, you'll see, heat is still being added. Temperature is not going up. This is called the heat of vaporization. Delta H vape. Heat of vaporization for water happens at the normal boiling point, so it's 100 degrees Celsius, and it actually needs 40.7 kilojoules per mole. So when you've got to the right temperature, you still have to put in 40.7 kilojoules per mole for every mole of water, every 18 grams of water that we're turning into a gas. Now, heat of vaporization in this case is positive because it's endothermic. So this is water energy that has to be added to vaporize it. But if you were to, that same amount of heat is involved when the condensation happens. The heat gets emitted. So if we were writing equations for H2O liquid into H2O gas, we would write delta H vape equals 40.7 kJ per mole. If we were writing it as H2O gas into H2O liquid, this is condensation, delta H vape would be negative 40.7. This is why steam burns you, because it releases heat. Oh, I had those equations written out. So just to give you guys some comparison, here are some other liquids and some heat of vaporizations that you could use. So you can see here water, heat of vaporization at the boiling point, 40.7. It actually does require some energy even at lower temperatures, but not, you can see it actually requires more energy at a lower temperature. Rubbing alcohol, lower heat of vaporization at the boiling point. Acetone, even lower heat of vaporization at the boiling point. Now, of course, the boiling point is even different. And diethyl ether, 34.5. So the lowest of them all. We'll look at how we can analyze the structure and tell what kind of intermolecular forces they have. But presumably, the higher the boiling point, the higher the IMFs. Let's do a problem. Let's do an example. So let's calculate the amount of water in grams that can be vaporized at its boiling point with 155 kilojoules of heat. So the question is, we've got 155 kilojoules of heat. I want to know how many grams of H2O can we vaporize? And to top it all off, we're at the boiling point. So the water is already is at 100 degrees Celsius. So we would need to set up some conversions. Mainly, we would need to be able to convert the kilojoules, right, of heat into moles of water, and then moles of water into grams. So the way that we're going to do this is we're going to say there are 155 kilojoules of heat. Using the heat of vaporization, I know that 40.7 kilojoules is required for every mole of water at its boiling point. So every mole requires putting in 40.7 kilojoules. 1 mole of water, so 2 moles of hydrogen, 1 mole of oxygen, off the periodic table is 18.02 grams. Do a quick calculation. .6 grams. Check the answer. Are the units correct? Does the answer make physical sense? Grams make sense, so the units are correct. Magnitude of the answer makes sense because each mole of water absorbs about 40 kilojoules, and therefore 155 kilojoules, should vaporize close to 4 moles of water, which, having a mass of about 18, almost 20 grams apiece, 4 moles of water is about 72 grams. Here, 68.6. It makes logical sense. You could do a type of problem with using this. I'll give you an example of another type of problem. A drop of water weighing 0.48 grams, right? I'll give it to you. 0.48 grams. This is water. Condenses on the surface of a 55 gram block of aluminum. Okay, the aluminum has an initial temperature of 25 degrees Celsius. It also has a heat capacity of 0.903 joules per gram degrees Celsius. So if the water condensing and the heat being released goes only towards heating the metal and not towards the air or other warming things up, which is the case in real life, what would happen? It goes in all directions. But if it only went towards heating the metal, what would the final temperature of the metal block be? These are the kind of questions that you are able to answer, using the heat of vaporization, and then coupling that with Q equals mc delta T. Okay, so in addition to the boiling point, we can look at the freezing and melting curves as well. So as the temperature of a solid increases, the thermal energy causes the molecules to vibrate faster, right? And then at the melting point, the atoms and the molecules have enough thermal energy to actually overcome the intermolecular forces that hold them together, and the solid turns into a liquid. Now, when ice melts, water molecules break free from the solid structure and become a liquid. As long as ice and water are both present, the temperature will be zero. I always like asking that kind of question on the test. Only after all the ice is melted will the temperature raise past zero. So I say, usually in my explanation of the difference between heat and temperature, I show a glass of ice water. So this is ice water, okay? And I say it's 0 degrees Celsius. And I say, then I add heat. And I add so much heat that all that's left is just this little sliver of ice. And I say, is the temperature higher, lower, or the same? And most everybody says, well, it's higher. And then some people will say it's the same. Nobody says it's lower. The answer is that it is the same. The temperature has not gone up. And so the reason is, right, the delta H of fusion, we call it. And this has to do with the heat that goes in, the energy required to make the solid turn into a liquid. And so that's where all this heat went. That heat went from turning solids into liquids, but it didn't go into giving them more energy. It just went from breaking them apart from each other so that now they can move around. That think of it as a Velcro. You've got to pull that Velcro apart, and now the molecules can move. The energy isn't even going right to their motion. It's going to breaking them apart. Okay. So, only after all the ice is melted are we going to see the temperature change. And so this flat part of the curve right here is that melting process. That is where the energy is going in. This is staying at zero until all of this happens. So this graph is showing us some ice that's going from -20 and then raising it to about 35 degrees. And you can see that flat part of the curve. So obviously a way to cool down a drink is to drop several ice cubes into it. As the ice melts, right, the drink cools because the melting is endothermic. The heat is absorbed when the solid turns into a liquid. So the melting of the ice is what actually cools your drink, not just your drink being next to some ice cubes. Okay, melting is endothermic because energy is required to partially overcome the attraction between the molecules. It doesn't completely overcome the attraction, right? Because then it would be a gas. It just partially overcomes that attraction. Freezing, on the other hand, is exothermic. Heat's released when liquids freeze. As water in your freezer turns to ice, it releases heat, which must be removed by the refrigeration system of the freezer. If the refrigeration system didn't remove that heat, the heat would actually warm the freezer and prevent further freezing. Okay, the amount of heat required to melt 1 mole of ice at 0 degrees is 6.02 kilojoules per mole. And if it is an exothermic process, then it is negative 6.02 kilojoules per mole. And you can see here a few different substances. The melting point of these much lower than 0 for water. Acetone, again, less intermolecular forces, melts at a much lower temperature. So at negative 94, it's turning into a liquid where water has to wait till it gets to 0. And then the heat of fusion shown for a few of these substances. So we should do a practice problem here too. Let's see what the problem is going to be. How about the amount of ice in grams upon melting absorbs 237 kilojoules? So we'll go 237 kilojoules. How many grams of H2O will melt? H2O is solid, right? So again, we're going to need to be able to take kilojoules into moles, moles into grams. This shouldn't be too difficult. So we've got 237 kilojoules of heat being put into the system at 0 degrees. Every 6.02 kilojoules will melt 1 mole of water. And 1 mole of water is about 18.02 grams. So if you do a quick calculation, 709 grams. So about 709 grams of water at that temperature would melt. Now, just to kind of show you how you could do a problem like this, but a little more complicated, let's say you were given a mole of ice, and I like to do 1 mole just because it makes the math easy. 1 mole at negative 25 degrees. And I want to know how much energy it takes, to get all the way up to 125 degrees. So what is the total amount of energy that you have to put in? So you'll notice that there are 5 parts of this curve. There's the increasing temp, the increasing temp, the increasing temp, and then the flat parts. For all of the increasing temps, we would go Q equals mc delta T, right? Because here the delta T is 25 to 0. Here the delta T is 0 to 100. And then here the delta T is 100 to 125. So for all of these parts, mc delta T, mc delta T. We have the delta T's. The C is the same. Actually, the C is different for all of these because ice has a different heat capacity than liquid water, than steam. But you could look all those up. So those you would just look up. And then the masses are the same. It's 18.02 grams, right? Because 1 mole of water. So you could find Q here, and Q here. Then we would have to find the other Q's. And these Q's are given by the delta H of fusion and the delta H of, delta H fusion here, delta H vaporization here. The flat parts, And this is basically, making your math easy again. We already know that this is 40 kilojoules per mole. So essentially, if we start with 1 mole, it's easy math. So it's whatever we got for Q, of course this is usually in joules, plus 6.02 kilojoules, plus whatever we got here, again it's usually in joules, plus whatever we got here, 40.7, plus whatever we got here. Yeah, so that's more of a Chem 1 problem. You're not going to have to worry about that. But that's the kind of thing we could do. We could actually calculate that, how much energy it takes to go from some low temperature to some high temperature. And it's doable. Sublimation is something that happens. It's a physical change in which a substance changes from a solid directly into a gas. When a substance, like carbon dioxide, sublimes, molecules leave the surface of the solid where they're actually held less tightly than on the inside. They become gaseous. Dry ice doesn't melt under atmospheric pressure at any temperature. It doesn't turn into a liquid at all. It just becomes a gas. Our pressure isn't strong enough for that to happen. At high pressure, we can get this to turn into a liquid. At negative 78 degrees Celsius, which is the temperature that this sublimes, this has enough energy just to become a gas. Let's see. One step. Regular ice actually will slowly sublime at temperatures below zero. So in your freezer or in really cold climates, ice or snow on the ground will gradually disappear if the temperature stays below zero. And in your freezer, in the ice cube tray, if you have one, ice cubes will slowly become smaller, even though the freezer is below zero. And this is because ice sublimes even out of frozen foods. It just becomes a gas, and then it just forms crystals somewhere else, usually on the surface of the bag or the container. Typical, inside of the lid on some ice cream, you got some sublimed water. So food that stays frozen for too long gets dried out, and the only way to avoid this is either deep freezing, so freezing foods to colder temperatures, like way below zero, or getting rid of any air in the container so that the water doesn't have anywhere to evaporate into. Okay, we've finally made it to the point in our discussion where we're going to look at the intermolecular forces. So let's just list them right off the bat, and then we're going to go through them. So they are dispersion force, dipole-dipole force, hydrogen bonding, and ion dipole, and in that order of increasing energy. So dispersion forces, the default intermolecular force. This is present in all molecules, all atoms. This is also called London dispersion forces, the older name. Dispersion forces are caused by fluctuations in the electron distribution within the atoms or the molecules. Since all atoms or molecules have electrons, they all have dispersion forces. The electrons in an atom or molecule at any one instant may be unevenly distributed. So if you look at the atoms here or this atom of helium, helium has 2 electrons. And most of the time, these guys are evenly distributed. They're on opposite sides of the atom. There isn't any one piling up on top of the other. But in some instances, we do see them on the same side of the atom. And if we were to look at that atom, it would have an overall negative side and kind of a positive side because of the way that those electrons have sort of moved to the same side. Now, we call this an instantaneous dipole or a temporary dipole. But what happens is that an instantaneous dipole on one helium atom can actually cause or induce a neighboring atom to also form an instantaneous dipole. And the fact that they can make each other do this leads to these little chain reactions of instantaneous dipoles forming. And this is what the dispersion force is. It's neighboring atoms that have instantaneous dipoles that are attracting each other. So let's say this guy started it all by having some negatives on one side, but got too close to its neighbor atom, and so that positiveness that belonged to this first atom drew the electrons over to the side, causing this atom to have now a positive and a negative side, which is going to affect a third atom and so on. And then, as this electron moves back over here, then the dipole goes away, these charges go away, so this charge went away, so this one goes away, and the electrons move back, and they all go back to normal. And then it starts over again, and it happens again. So what kind of things affect how easy or hard it is to have dispersion forces? Well, let's talk about it. The magnitude of this dispersion force depends on essentially how easily the electrons can polarize. How easily can they move to one side or the other? How easily can these instantaneous dipoles form? And one of those things, the main one actually, is the size of the electron cloud. The bigger the electron cloud, the easier it is to move those electrons around because they're not as close to the nucleus. They're not as tightly held by those positive charges. And one thing we see on the periodic table, right, is that as we move down any column or row, the electron cloud gets bigger and bigger and bigger, right? This is a 1s, and then a 2s, and then a 3s. So within just a column, the electrons are in bigger and bigger clouds on the outside. Therefore, they can be polarized more easily. So electron cloud matters. Now, so does molar mass. Molar mass can kind of give you an idea of how many electrons there are. Usually more molar mass means more electrons. It's not the best way to determine, who's going to have more molecular forces, intermolecular forces, but it can be a guide. And so to kind of show you a comparison here, you can see as we go down the noble gases, they do have bigger and bigger masses. Of course, they also have bigger and bigger electron clouds, and you can see their boiling points also change quite dramatically. Helium has the lowest boiling point, and then neon, which only has, this has 2 electrons, this has 10 electrons, but this was the last electrons are in the 1s, here they're in the 2p. Remember 2s, 2p, outer shells. Just because of their size, we can see an increase in the boiling point, which means an increase in the intermolecular force, because it takes more energy now, a higher temperature, to get neon atoms to separate from each other, to get neon liquid to become neon gas. And this is true for melting points too. Melting points and boiling points would follow the same exact trend. Okay. So that's looking at the dispersion force that's in everything. Now let's look at more selective forces. So here's the dipole-dipole force. Dipole-dipole exists in all polar molecules. So this is polar only. This is why we spent time in chapter 10 trying to figure out if things were polar or not. Polar molecules have permanent dipoles, unlike the instantaneous ones that are fleeting. These are permanent, and this has to do with 2 things. This has to do with electronegativity differences. This also has to do with your shape. So this is, again, go back to chapter 10 and look these things up if you don't remember it. So all molecules, including polar ones, have dispersion forces, but in addition to dispersion forces, so, right, all dipole, so this is dispersion included, dispersion forces included, now there's an additional force. And this one is, again, polar. So if you're a dipole, it means that you have permanent charge separations. And when you bring 2 dipoles near each other, just like if you bring 2 magnets near each other, we get attraction. Now this isn't as strong as an Na plus Cl minus's attraction to each other, the one that holds this together as an ionic compound. And again, this is with all of its electrons. But a negative charge and a positive charge are the 2 strongest things you can, well, aside from a 2 plus and a 2 minus. So scratch what I was about to say. The size of these full charges is gonna affect the strength of the attraction, but these are only partial charges, and so they aren't as strong as the ionic bonds. And we have ways of quantifying how strong these partials are, but that's beyond the Chem 20 class. So anything that's a dipole is going to have dipole force and increased things like increased boiling point and melting point, increased viscosity, increased surface tension, decreased vapor pressure, right? Whenever we see dipole forces now being introduced where things maybe only had dispersion forces before. So here we can look at 2 different compounds. Ethane has dispersion only, and formaldehyde has dispersion and dipole. And so we can see here now, again, we can look at this structure and we would come to dispersion only because we would look at the electronegativity differences between these atoms, and they aren't enough for us to draw a polar bond, to say that this is polar, or to draw a little dipole arrow or anything like that. There wouldn't be enough there. So it's a nonpolar molecule or nonpolar bond, and then it also has the right shape for that, the nonpolar shape. Whereas this one, this is a polar bond, so we would draw that. Now the CH bond isn't polar, but unless we have polar bonds in all 3 directions, these don't cancel out. So this does have an overall negative side and an overall positive side. And again, remember, go back to your trigonal planar. Looking at the three atoms, they're not the same, so this is polar. Look at the difference in the boiling points. So remember, being a liquid warming up, so like going from negative 100 warming up, this one boils at negative 88 with only dispersion forces, and then this one boils at negative 19 with added dipole forces. We know water's way up here, right, at 100 degrees, positive 100, but it also has an additional intermolecular force. Plus these two, dispersion and dipole, it also has a third intermolecular force. Water does. That's probably what makes it a liquid when everything else is a gas. So again, just some comparisons here. Now again, the dispersion force is roughly comparable because they have basically the same number of electrons. And so the force due to dispersion is probably equal. And so the main difference here is because one has a dipole and the other doesn't. Review this if you need help figuring out if your molecule is polar or not. Obviously, you need to draw a good Lewis structure first. If your Lewis structure is wrong, then you're going to be looking at these and it's not going to make sense. Okay. I had this up here for a reason. Went back a slide. And so when we talk about things being polar, in general, when things are polar, that means that they're mixable or miscible. Miscible is spelled like this. They're miscible with other polar substances. So for example, water, which is polar, is miscible with rubbing alcohol, which is also polar. But water is not miscible with pentane. Pentane is non-polar. Similarly, water and oil don't mix, right? Oil is non-polar. Water is polar. Non-polar, polar. These guys, this would be hexane or octane, something like that. Pentane, this would be oil. And so oily hands or oily stains on clothes can't be washed away with plain water, right? We need to use soap for that. Okay. So yeah, definitely look at this and try to figure out, again, when you're given a formula like acetone, acetone is C2H, here's acetone. Wait. That's acetone. So this is C3H6O. Right? Bunch of nonpolar bonds, bunch of nonpolar bonds, nonpolar bonds, nonpolar bonds, polar bond. And so something like this, usually that C double bond O in anything you find it in is going to be polar. So acetone molecules are polar. They just don't have as much of intermolecular forces as water does. But again, when you draw these things out, you want to stay true to the trigonal planar, tetrahedral sort of geometries. I don't think you're going to be asked to draw any molecules though. Let's look at the last intermolecular force. Second to last. The last one actually is just a combination of ones we've already seen. This is hydrogen bonding. Polar molecules that contain hydrogen atoms bonded directly to fluorine, oxygen, or nitrogen will exhibit an additional intermolecular force called hydrogen bonding. So that's an H attached to an F, an N, or an O. The electronegativity difference is so great with these that this bond that they actually form is really, really polar, super polar. And it's like, these are the most polar ones. And as that, as a super dipole force, it will create this really strong attraction between the hydrogen in each of these molecules and a fluorine or oxygen or nitrogen on a neighboring molecule. So in addition to having to be on one of these three atoms, one of these three atoms also is the reason why we get a hydrogen bond. So let's take a look. So in this first molecule of just HF, we see that there is a hydrogen. Let's look at the middle one instead. We see that there's a hydrogen bonded to a fluorine. So that's going to make this very polar. Hydrogen's going to be sort of missing its electrons completely. Fluorine will have all the electrons. Now, if there was an oxygen, a nitrogen, or another fluorine around, that fluorine would see that hydrogen as partial positive, and being fluorine and being kind of negative, it's going to form a bond with it, or an attraction, right? Kind of like an ion, like two ions together. And again, this could happen with a nitrogen as well. If there was a nitrogen around, so if this molecule wasn't here and there was a nitrogen, like an ammonia molecule, this guy would form what we call a hydrogen bond. And so anytime we see hydrogens directly attached, and you can see them even here too. So a fluorine would form a hydrogen bond with these H's, because these H's themselves are attached to nitrogens and would be able to participate in hydrogen bonds. So it can be a complex little pattern of interconnected molecules. Look at this other one. This is methanol. Methanol. There's an OH, so an O and an H directly attached, and then in neighboring methanols, there's an O that's able to hydrogen bond. I'm going to show you how water does it in a second, so you can see why water even has a higher boiling point than methanol. But let's take a look at methanol. Methanol and ethane are roughly the same in mass, not much of a difference, so dispersion forces should be roughly the same. Methanol doesn't have, methanol's a dipole. Methanol's a dipole. It's got a negative side, and it's actually technically got two positive sides, so maybe it's not technically called a dipole, but it is polar for sure. So it's polar. Polar molecules will participate in dipole-dipole interactions. Ethane doesn't have any of that, so this is dispersion, check. Dipole, no. H bond, no. There's no H's attached to O's, N's, or F. Methanol, dispersion, of course, everything does. Dipole, well, it is polar. Dipole, so we're going to count that. It's polar. And then H bond, yes. It has an O and an H directly attached, and then if this was a solution of just methanols, then other methanol molecules, like this guy, could form hydrogen bonds. So this could actually form two hydrogen bonds if they line up like that. Difference in boiling temperatures. Ethane boils at -89 as you increase the temperature of the liquids from, let's say -100 going up. And then this one, methanol, +64. So big difference, big jump in that, because it has that hydrogen bonding. We saw that not that long ago in the previous example. I think it was formaldehyde was polar compared to ethane. And formaldehyde, which had a dipole, still was -19.5. This one, having a hydrogen bond, makes it 64. So it's much more energy required. Let's look at water. So here's water. Water has strong hydrogen bonds, and it forms multiple hydrogen bonds with each other. And it's actually the reason why water actually, when it freezes, becomes less dense, when most things, when they freeze, become more dense. They pack together and become more clumped up. Ice floats because water becomes less dense. And the reason ice floats is because when water freezes, it optimizes the hydrogen bonds. It spreads out a little bit instead of packing together closely, because if it spreads out a little bit, it can get hydrogen bonds between all the O's to a bunch of other H's, and it maximizes these little connections. So here we go. We've got hydrogen bonds in water. You can see each water molecule can actually make 2 hydrogen bonds just from its O, and that's with the lone pair electrons. And then, of course, other water molecules can hydrogen bond with the H's. So every water molecule itself can make 4 different hydrogen bonds. Okay, and that raises the temperature, of boiling of water, right, 100 degrees. Um, okay, ion dipole forces, which are the last type, exist between ions and dipoles. So water is a good example here because water is a dipole. Water itself has a negative side and a positive side, and it can surround ions easily. The oxygens, which are all negative, like to surround positive ions. The hydrogen side, which are all positives, will surround negative ions. And so water is really good at dissolving positively charged and negatively charged molecules, ionic compounds, because of this property. Now, we're going to look at in chapter 13 why some solutions form and some others don't. We looked at that a little bit in chapter 7. But, why does sodium chloride dissolve but silver chloride not dissolve in water? We got to look at is water providing as strong of an energy bond as silver would be providing to chlorine? And that's ultimately going to be the deciding factor. Who can get to a lower energy system? Does chlorine have a better chance of being low energy with silver, or does chlorine have a better chance of being low energy with water? And every molecule that dissolves or tries to dissolve, they need to kind of figure that out. Okay, so I think after that, hydrogen bonding, I just wanted to mention that this is part of our DNA. DNA molecule is composed of thousands of repeating units called nucleotides. Each nucleotide contains a base, which are adenine, thymine, cytosine, or guanine. These are our A, T's, C's, and G's. And then the order of these bases along the DNA encodes the instructions for how our body makes proteins. So DNA actually consists of 2 complementary strands that wrap around each other in a famous double helix. And each strand is held to the other by hydrogen bonds. And these occur between each strand. And you can see here that the adenine hydrogen bonds twice with the thymine, cytosine hydrogen bonds 3 times with the guanine. And we can actually DNA can replicate itself because each base has a complementary partner. Yeah, okay. I was going to say something else. About solids. Let's talk about solids a little bit. Solids can be crystalline, which is a well-ordered array of atoms or molecules. Crystalline solids can then be divided into a couple of other categories. So we mentioned solids can be amorphous or they can be crystalline. So as far as crystalline solids go, there are 3 types. There's the molecular types, there's the ionic types, and then there's the atomic types. Now, as far as these go, the molecular solids are those that compose units of molecules or molecule units. So ice, solid water, dry ice, solid CO2. These are examples of molecular solids. Molecular solids are held together by intermolecular forces. These would be dispersion forces, dipole-dipole forces, hydrogen bonding. And so like ice is held together by hydrogen bonding, dry ice is held together by dispersion forces. Molecular solids tend to have low to moderately low melting points. So, melting at things like -78 for dry ice sublimes, or 0 degrees Celsius for water. As far as ionic solids, these are formula units, right? The smallest electrically neutral collection of cations and anions. So like the formula unit NaCl, even though we know that every Na has a bunch of Cl's around it, and every Cl has a bunch of Nas around it, in the crystal. We always just say NaCl instead of Na 1000, Cl 1000. Ionic solids are held together by the electrostatic attractions between those cations and anions, and so these tend to form these big lattices of alternating cations in like 3-dimensional big blocks. And these are ionic bonds, and since these are much stronger than any of the intermolecular forces, these have higher melting points. So things like 801 degrees Celsius for like carbon disulfide, where a molecular solid with the same molar mass might melt at like 110 or negative 110. You know what I mean? So sodium chloride melts at 801 degrees, carbon disulfide molecular at negative 110. So ionic, much, much higher. Atomic solids. Now, atomic solids are those whose units are composed of individual atoms. So the units are individual atoms. And some examples of these would be diamond or iron or solid xenon, for example, diamond being carbon. Now, atomic solids can be divided into three categories. They could be covalent atomic solids, they could be non-bonding atomic solids, or they could be metallic atomic solids. And each is held together by a different kind of force. So the covalent atomic solids, these are like diamond, are held together by covalent bonds. So a covalent bond we know is sharing of electrons, and in a diamond this happens in in a tetrahedral geometry. And so a diamond crystal can be thought of being a giant molecule held together by covalent bonds. Since covalent bonds are strong, covalent atoms or covalent atomic solids tend to have high melting points. Diamond is estimated to melt at about 3,800 degrees Celsius. Diamonds also spontaneously decompose. Diamond, which is just carbon solid, will become carbon gas spontaneously. It's just a really, really, really slow reaction, and I just wanted to mention that. It takes a really long, like thousands of years for that to happen, but it does happen spontaneously. Okay, I think I had a picture of a diamond. Yeah, there's a diamond picture. Non-bonding. Let's talk about non-bonding. Non-bonding atomic solids are those such as like solid xenon, which are held together by relatively weak dispersion forces. So these would be non-bonded in the sense that they're not sharing electrons. So xenon atoms have stable electron configurations, so they don't form bonds. Consequently, solid xenon, like other non-bonding solid atomic solids, have very low melting points, like negative 112. And then we have the metallic atomic solids. Now these metallic atomic solids, such as iron, silver, lead, these have variable melting points. Metals are actually held together by metallic bonds. And in the simplest model, we say this consists of a positively charged ions in a sea of electrons. So all of the metal ions are just sort of the positive bits, and then the electrons just sort of exist in kind of a sea. They say they don't belong to any one atom; they just kind of float around. This explains why metals conduct electricity really, really well, because the electrons are just sort of there and not attached to any one particular atom. Metallic bonds are of varying strengths, with some metals like mercury having melting points below room temperature, and other metals like iron having extremely high melting points like 1800 degrees Celsius. So again, the sea of electrons, metal cations surrounded by those electrons. Now, water, wanted to remind you guys of why water is so cool. It has a low mass, 18.02 grams, but it's a liquid instead of a gas. It's really high boiling point. We know by understanding its structure and knowing about the intermolecular forces that bent geometry gives it the highly polar nature. Or bent geometry and the highly polar bond, the OH bond, results in this polar nature. The fact that it has two OH bonds allow water molecules to form strong hydrogen bonds with other water molecules. This gives it that high boiling point. And then its polarity, high polarity, also allows it to dissolve lots of polar and ionic compounds. So it's the main solvent of living organisms. We transport nutrients and all other stuff through our water. Life's impossible without water, as far as we know, and in most places on Earth where liquid water exists, life exists. So yeah, it's pretty remarkable. And I mentioned even how it freezes, how when water freezes, if water froze in a pond and then sank, like most other solids do, eventually, right, the whole pond would freeze through and all life in it would die. But instead we have, icebergs, and we have fish living inside of a frozen lake, insulated from the winter, because of that. Yeah, okay. Well, I mean, it's also because of water that we can't, like, we don't want to have our pipes bursting and stuff, because water can actually, water freezing is actually bad for life, because our cells, right? Our cells don't really grow very well when water freezes in them and then expands and then pops our cells. So it's hard for us to kind of deal with frozen water. But in outside of our bodies, the remarkable nature of water is pretty evident. Now, what did I have at the end here? I wanted to talk a little bit about a review. So just we went over properties of liquids and solids. We went over the manifestations, surface tension and viscosity. We talked about evaporation and condensation and what vapor pressure was. And then we went over like melting and freezing curves, as well as sublimation. We went over the types of intermolecular forces. There's dispersion forces, there's dipole-dipole forces, and hydrogen bonding. And then the last one was just ions with dipole-dipole, or ions with dipoles, so ion-dipole. And then we went over the types of crystalline solids, the molecular solids, the atomic solids, and the ionic solids. And then a little bit about water, because water is really cool. So hopefully that helps, and hopefully these learning objectives help. But that was a long chapter. This chapter really goes well with chapters 9 and 10. So hopefully, if you're struggling at all, go back to 9 and 10, figure out valence electrons, figure out Lewis structures, figure out polarity, and this will help a little bit. Moving on in 13, 14, 15, 16 direction, we won't be really talking about this too much in terms of intermolecular forces, but it may pop in, here and again. All right, guys. See you in the next video.